please.
Thank you. Hello, everyone. So my name is Vincent Lecours. I'm a professor of marine remote sensing and geospatial analysis at the University of Florida in the US. And today I'm going to be presenting about some exploratory work that we've done to see whether we could use multiscale geomorphometry to delineate and identify different types of coastal habitats in Florida. So just to give you a little bit of context, coastal habitats in Florida provide a wide range of what we call critical ecosystem services. For example, they protect the coast and the local communities from erosion and storms. They provide a lot of opportunities for tourism and outdoor activities. They provide habitats for other species, for example, many fish that then enhance our fisheries. However, many of these habitats and the services they provide are facing extreme pressures. So we have a lot of unsustainable tourism, inadequate protection and management, climate change and pollution. And despite an increase in policy and conservation measures in the last decade, it's been shown that a lot of those measures often miss the target. And there are two main reasons for that. One is that we realize that we actually don't know a lot about those habitats, so it becomes difficult to make conservation measures that are adequate for those habitats. And also there's a lot of political and economical pressures on those policy and measures. So current ongoing restoration and monitoring efforts don't have baseline data against which to quantify success. So there's really a need for a frequent, effective, and comprehensive mapping and monitoring method in Florida to map coastal habitats. So in the last few years, my lab has been implementing and developing a multi-scale framework for coastal habitat mapping and monitoring using remote sensing. So we have different projects, for example, to detect different types of coastal habitats at the state level. So here you see the state of Florida. Then we do a lot of kind of intermediate scale estuary level studies that look at the ecosystem itself. And then we do some fine scale studies to really understand how fine scale structure of different habitats contribute to a healthy ecosystem. So today I'm going to be focusing really on that intermediate level, estuary level, where we have a mix of different habitat types. It's very important when we're looking at these kind of environments to adopt an ecosystemic perspective, because there's a lot of, for example, here you see some oysters on top of a mud flat with a salt marsh fringing on it. And from a year to the next, there can be changes. For example, if the oysters become unhealthy, they can erode, and then that habitat could transform into a full mud flat, which could then become colonized by the salt marsh. So when we do temporal monitoring, it's important to really look at the dynamics of the different types of habitats. So the project I'm going to be talking about today started with this work from Michael Espriella, my co-author on this talk. Basically, Michael used DJI drone data to map Little Trout Creek, which is a little estuary on the west coast of Florida. This is the orthomosaic that was constructed using the drone imagery. And you can clearly see on that image different type of habitats like mud flats here. We have different salt marshes with some vegetation on top of it, and oyster reefs. And these data have a very high spatial resolution. So we have an example here of a marsh. The spatial resolution of the orthomosaic is 6 millimeter. So very, very fine resolution. You can see a salt marsh with oysters around it, our ground targets. And then you can see different type of habitats like the mud flats and the oyster reefs. Here on the oyster reefs, we even see the scars from boating propellers. So intertidal habitats are those habitats that are under the water at high tides. So they then become susceptible to damage from boats, but then at low tides, they appear above the waterline. So Michael used an object-based image analysis. So for those of you who are not familiar, basically we can regroup homogeneous pixels into objects, and then it's those objects that we classify, and obtained a relatively simple habitat map where the classification recognized the different types of habitats, so marsh, mud, and oysters. Michael's classification had an accuracy of about 80%. And we didn't find that that was high enough for our purposes. So we tried to investigate a little bit why we couldn't get a higher accuracy. And one of the main reasons that we found is that water and the movement of the tides cause spectral changes and artifacts in our orthomosaic. So if I bring the mosaic back here, you can see those kind of linear artifacts across the mosaic. And this is caused by the fact that we have a very small window of time at the lowest tide to collect our data. So the difference, as we start surveying in the south part of the study area, basically the tide is going higher and higher, which causes those differences. And also, a wet oyster is going to look different spectrally than a dry oyster. So it really complicates the entire classification process when it's based solely on spectral information. And then even if visually speaking, different habitats look different to us, to the computer, the spectral response is quite similar. So basically our conclusion from that paper was that using only spectral information may not be enough for our needs. Because if we want to do accurate temporal monitoring where we can detect really where oysters are, where mud flats are, and where vegetated salt marsh are, we need to have a better accuracy than 80%. So we wondered, what can we do to increase that accuracy? And the first thing we thought about is to use structure from motion photogrammetry to produce a digital surface model from our imagery. So here you have an example of a DSM that we can produce, and we mask the water area in this case. And then simply derive different terrain variables to try to see if the topographic information can assist the spectral information when we classify our different habitats. However, our feature space optimization as part of the object-based image analysis showed that the terrain variables were not contributing much to the classification process. And the main reason for that is that we just use a default kind of 3x3 window of analysis in GIS software, which with a 6mm spatial resolution means that we're only characterizing terrain characteristics at a very, very fine resolution scale. So about, 1.8 centimeters. But what we know from a lot of different fields, whether it's ecology or geomorphology, well, we know that different habitats will be characterized by different features and patterns that relate to different ecological processes at multiple different spatial scales. And it's well known in ecology that single scale studies often fail to capture the relevant patterns and processes. So our solution here was to implement multiscale analyses. So our question was, can we use multiscale terrain characteristics to extract a topographic signature for our different habitat types in order to, that would allow us to improve our classification accuracy? So we used the platform Whitebox Tools, which was developed by John Lindsay, one of our colleagues in Ontario. John and his team throughout the years developed many different multi-scale tools, one of them being a multi-scale roughness tool, which basically you provide the tool with a range of window of analysis. And then for each pixel, the tool will calculate roughness at those different windows of analyses, and then will report two outputs, one being the maximum value of roughness that was calculated, and second, the scale at which that maximum value of roughness was calculated. So we use that tool, multi-scale roughness, on our data set. We use analysis scales varying between 3, so a window size of 3x3, which is the smallest we can do, and 9,750, which corresponds to an analysis distance ranging from 1.8 centimeters to about 60 meters. We picked 60 meters because it was the biggest, the size, the length of the biggest features we found in our imagery. And this is the main result. So we can see, for example, here on the right that we have areas of very high roughness and areas of lower roughness. And the scale at which that roughness was measured also varies widely throughout the study area. So then we use our initial classification to extract statistics for the different habitat types. So we tried to understand really the patterns of multi-scale roughness for each habitat type. And if I summarize them, basically we found that our salt marshes had the highest values of roughness that was found at the finest scales. And that makes a lot of sense because we had a digital surface model that captured the top of the vegetation that covers salt marshes. So that vegetation really creates that fine scale, high roughness. Then for our mud flats, it was kind of expected. We found our lowest values of roughness, and that roughness was measured at the broadest scales. And for oysters, we had relatively high roughness found at relatively fine scales, but not as high or fine as for our marshes. So by using different statistics, for example, the median scale of roughness for each habitat type, and knowing our spatial resolution, which was of 6 millimeters, we were able to kind of determine an ecological scale at which the patterns characteristics to each habitat types could be captured. And we got 1.5 meters for the marshes, around 13 meters for the mudflats, and 5.3 meters for the oyster reefs. So these kind of preliminary results tell us that we can indeed differentiate different coastal habitats using their multi-scale topographic characteristics, which means that in theory, we could be developing topographic signatures for each of those habitat types. So I just want to show you a few examples here. So, I've showed you that image quite a bit. We have a small patch of salt marsh surrounded by high density of oysters and then oysters covering a mudflat. And we can really see in the multi-scale roughness metric how it captured very, very well the difference between the marsh and the surrounding habitats. Then here we have a mudflat, and what's interesting here is that if we only use the spectral information, it's really difficult. Actually, we can't really see that there are individual oysters on top of that mudflat. And even if in our digital surface model, it's not very obvious, but the multi-scale roughness tool really captured those individual oysters, which is quite exciting from an ecological and management point of view, because it means that we might be able to use these metrics to count or estimate the abundance of oysters. And then here we have an oyster reef with different densities. So we can see we have higher density on the surrounding of the oyster reef. And that was pretty well captured in the multi-scale roughness tool. So in conclusions, I think that's a good example of how geomorphometry can contribute to answering marine and coastal ecological questions. The potential to develop topographic signatures for different coastal habitats is promising to address some important surveying and sampling challenges associated with intertidal environments. However, there's still a lot of work to be done. So our next step is to extend our analysis to other multi-scale terrain variables. So in white box tools, we have access to tools that calculate, for example, a multi-scale topographic position, a multi-scale difference from mean elevation, or a multi-scale topographic anisotropy. And we had actually done that work. However, we put the analysis on hold because we decided to, Michael, my co-author, redesign a survey of that same area, but using a LiDAR system. So we want to compare results from a digital surface model and a digital terrain model computed both from LiDAR data and from structure from motion photogrammetry. The assumption here is that if we remove the vegetation on top of salt marsh by using a digital terrain model, that our oyster reefs are then gonna come out as the more rough kind of habitat. And then we'll integrate all these multi-scale variables into our feature space optimization workflow and object-based image analysis. And finally, we're really interested in comparing the topographic signature of those oysters that sometimes go above the waterline, so those intertidal oysters, to that of subtidal oysters, which are those that are always underwater. And actually tomorrow we're starting field work. We're going to use an autonomous surface vehicle to collect acoustic remote sensing data, so sonar data on top of oyster reefs, which is going to give us really a good digital surface model of the underwater component of the reefs. And we're also going to be collecting underwater imagery data using a remotely operated vehicle to see if we can use underwater photogrammetry to get comparable information and data. So that's it for me. Thanks for your attention.